Well, hello, Kira. Did you figure out your like simulation stuff?
I downloaded on Homebrew, but I'm not very good with
Dude, me neither.
oh, so I actually have no idea how to run it. So it's okay. I just typed it into Google Docs and I'm gonna figure it out later.
Yeah. Hey, another person. Yeah, by the way, I don't know if I said this, Kira, but we'll probably get started at like 3:05. If people don't join by then, they'll probably.
Okay, sounds good.
Bad news here. It's probably going to be like 5 people.
Oh, that's just too bad for you, right?
I mean, I'm going to give the whole presentation anyway.
Yeah, I'll see if I join the other thing on my iPad. That way I don't leave this one.
You can leave this one if you want. It's okay. I will be all right. And Kira's going to get some great information.
Okay, well. All right.
Oh boy, another person. Welcome. Oh yeah, I forgot. I didn't say it, but I don't to do the live programming. I don't have Cordis installed on my tablet, so you guys don't get to see my face. I'm sorry. And I have no webcam. That's why I can't do it.
Is this an event with IEEE at UCSD?
Yes.
Cool. So
Why do you ask? Where'd you come? How'd you get this link if not the Facebook page?
Someone had sent it to me, so
Oh, well, yes. Do you go to UCSD?
I do not actually.
Well, makes no difference to me as long as you're interested in IEEE.
Yeah, I go to USC, and I'm interested in Verilog and stuff.
Dude, me too.
Yeah.
Although
What?
making this workshop, see, Verilog's hard.
Yeah.
We'll get started in about a minute, by the way, guys.
Are we gonna be like, or are you gonna be messing with model sim?
Yeah. The software I'm familiar with because I took one class in Verilog is Cordis Prime, and then they use, I think, the simulators with Model Sim Altera.
Can you save me?
Save
I'm
you?
I'm taking that class right now and I need help.
Is it EC 111 or CSE 140?
140.
I don't know exactly what 140 is because I did EC 111. You can do it, dude. You're gonna learn so much right here. Actually, I don't know how relevant this is to the actual class.
I just need help getting set up and basic syntax, but I don't know if this is the right workshop.
This will be a decent place because I do plan to do some live programming with you guys, which is not going to go well. Live programming, I feel like, never does. But you should be able to see some syntax and stuff. And feel free to ask questions about like the syntax and things like that as we go.
Okay.
Okay, let's go ahead and get started. I think I want to share this entire screen. Yeah, you guys don't get to see my DMs there. Alrighty. Let me, I guess I can have this off there, right? It doesn't hinder at all. All right, so let's go ahead and get started. Welcome. I see a couple, well, actually, I think maybe only one person from the part one system Verilog, which is fine. You guys, it builds off of what we did in part one. Basically, it's the idea of finite state machines and syntax. So if you're familiar with system Verilog in those parts, you should be fine to jump right in. But this is part two, building off of that. My name is Chase Bastion. You guys can see on the thing, I'm the IEEE, well, IEEE Tech Chair for UCSD. And yeah, let's go ahead and get started today on what we're going to be working on. So today's goal originally was a fully functioning I2C module in system Verilog and stuff. That turned out significantly harder than I expected. So today's goal is simplified I2C module. In fact, the end goal of today is to write a master and a slave module. So the master is going to only be in write mode, and we're going to send the address and 1 byte of data to the slave module, and then the slave module's job is just interpret that. And if we get that far today, awesome. And then at the end, I'll give you guys some recommendations if you're still curious about like I2C and implementing it further to like the fully fledged module. But I do not have a current working one myself, so just these suggestions and things. So let's go ahead and get quick and get into what I2C is. So I2C stands for Inter-Integrated Circuit, and it is a circuit communication protocol between integrated circuits and whatever processor you're using. So for example, if you're working on some kind of system and you guys can see the slides, by the way, right? I'm not sharing with the wrong screen.
Yeah.
Awesome, because my other screen, like the Zoom thing is on my other screen, and that would be the wrong screen to share. Okay, sorry, continuing forward. So if you have a system that works, you have your like central processing microprocessor, and then a bunch of peripherals. I2C allows you to basically get data from those separate integrated circuits. So for example, if you had a sensor connected to your microprocessor, it would allow you to get the sensor data from your sensor into the microprocessor. So it's a super common communication protocol in just like industry and anything with like systems and stuff that work with multiple integrated circuits, because you need to communicate between them, and this is a very easy way to do it. So a couple of the plus sides of what I2C is and why it is used so commonly is it's pretty easy to implement in terms of actual hardware. So you actually only need 2 data lines between your microprocessor and your ICs, your things you want to communicate with. And in fact, you only need two input output lines on your microprocessor, the SDA and SCL lines for up to like 100 different slave devices that you'd want to talk to. So very efficient in terms of hardware as opposed to alternatives. Like for example, I think SPI uses a lot more like hardware, like just physical wires to connect things. So that's one big like upside. And the other upside of I mean, I'm sure there's more than one upside of I2C. The other notable upside and benefit of I2C is the ability to connect multiple slave devices to one master. So if you have one master who drives the SDA and SCL lines, you can connect up to 2 to the 7th slave devices, because each slave device has an address that's going to be 7 bits long. That allows the device to determine if it's being communicating with the master or some other devices. And you might be like, well, how the heck am I going to connect 100 devices to 2 different lines and have them not interfere or anything? And that's down to the implementation of I2C, which is that every I2C slave will be connected to both the SDA and SCL lines in a open drain configuration, which is the image you see here. So the actual output from the slave, the data it's trying to communicate, will be the input into this transistor. And then the SDA and SCL lines will be sampled after the resistor and before the transistors. And so what this does is if the output of a slave device is low, so the voltage on the gates or the transistor's gate is low, that means the transistor will operate basically as an open circuit, meaning there's no direct connection between VDD and ground. And so V out, because there's no current flowing through this resistor, will get pulled up to the VDD voltage, and it'll be read as a high. In I2C, it doesn't actually read the voltage. Instead, it reads the state of the impedance, basically. So because this operates as an open circuit, the impedance of the total circuit is really, really high. And so it reads that really high impedance as a high value. So by default, if nothing is actually trying to influence the SDA or SCL lines, it will default to the value 1 because of that, because they're all connected in this fashion. Or specifically, not the value 1, but a high impedance, which we interpret as 1. And then if the slave device, any slave device, is driving or trying to hold the SDA or SCL lines low, it will apply a high voltage to the transistor gate. This will act as an open circuit and provide a direct connection between ground or source power to ground. And then because we're sampling SDA and SCL after the resistor, this acts as basically all the voltage will drop over the resistor, and we will read V out as a low voltage then. So the way that we're able to connect a lot of devices is that if any one device is pulling this transistor, like activating it so that it pulls the things to ground, then the entire SDA and SCL line will be read at 0. And if any other devices, like it doesn't really matter what they're doing, if even one is doing that, it's pulling it low. Whereas if no devices are pulling it low, it'll be read as a high. So in practice, that means if you have multiple slaves, if it basically, in theory, one should only be operating at a time and the other one shouldn't have an effect. But if they accidentally do, it means that the one slave that's pulling it low will override, and basically so the low signal like proceeds, which in practice, it's not going to happen, hopefully. But that allows us to have the other devices not do anything to the line when they're not actually communicating with the master. And then only the slave that's being communicated with will control the line, and the other ones won't have any effect on it. So that's how that feature works and where it comes from. Yeah, hopefully that's a little bit clear on what I2C is. We're going to get into like actually what the waveforms are and like the specifics of it in a second, but that's just the general overarching concept of what I2C is and what makes it nice. Any questions on like what I2C is, what it's used for, and like any benefits or drawbacks before we get into the nitty gritty of like what a waveform for I2C looks like? Okie dokie. By the way, I do not have chat open, so all right, there we go. Chat's open. So if you have questions in chat, feel free. If you have questions, also feel free to just unmute. That would be the preferred way if you guys can just unmute and ask me. But okay, so that's just what I squared C is and what it looks like. So let's get into how we're actually going to generate I squared C waveforms and interpret them. Just gotta click, there we go. So I squared C, there's like two really important bits, the start and stop, that actually tells like that the master will generate to tell the devices that a transaction is going to happen. So the start sequence is anytime the SCL line is held high and the SDA line changes. So what this means is that anytime we're changing SDA, which is how we're going to transmit our data, we have to make sure, according to the specifications of I squared C, to do that change when SCL is low, or else the change will be caught while SCL is high and be interpreted as a start or stop sequence, which obviously you don't want to generate in the middle of your program. It'll get like weird, go back to like restarting states and stuff. One thing I should mention, by the way, is the default, I mentioned it a little bit in the idea of the open drain here, is that if nothing is actually driving the line, then the line is interpreted as a high by default, which means that the idle of our I squared C, both SDA and SCL, if we're not actually trying to write any signal to it, will default be high. So to trigger a start will be, SCL will just stay high as it normally would, and then trigger a start, we just need to pull SDA low for one cycle. And that will let the device know we're trying to start a transaction. And then on the other side, once we're done with a transaction and we want to stop and like close everything up, the stop bit is very similar. While SCL is held high, we just need to transition SDA from 0 to 1. So basically just the opposite of each other. So those are the start and stop bits. And then in between every start and stop bit, we're going to be sending the address of our device and the data of our device. So the process of sending the address is immediately after the start bit, SCL will become a clock, like it'll just be the clock of whatever you're sending through, which is what all the devices are going to sample based on. And so once SCL becomes a clock, every clock cycle, the SDA, you have to hold the value over that entire clock cycle of whatever value you're trying to write. So all the addresses of the slave bits in I squared C are 7 bits long. So immediately after the stop bit, the next 7 bits are going to be the address of whatever slave device you're trying to communicate with. And then after, so that's what our implementation is. It's simplified today. We're only going to be doing start bit, 7 bits of address data, 8 bits of data, and then a stop bit. But a fully implemented I squared C device, it will have the start bit, and then immediately it'll be 7 bits of address data. The 8th bit tells the slave devices whether the master is initiating a read or write transaction based on whether the read or write bit is 1 or 0. I believe it's 1 for read and 0 for write, but it's not very important. You just change it in your logic, but I could be wrong. So take that with a grain of salt. But so the 8th bit just tells read or write to the slaves, and then the 9th bit, so technically every data transaction, whether it's address or data we're sending, has a 9th bit that is the acknowledge or not acknowledge bit. This also is not implemented in our simplified version today. But what it does is it's actually written from whatever device is acting as a slave. So if you're in write mode, the slave will obviously be the slave. If you're in read mode, the master kind of becomes a slave and reads the data from the slave device. So that 9th bit is made by whichever device is receiving the data. And so a 0 is an acknowledge bit, meaning that it got all the data fine, or that, like in the case of when we're sending the address, it means that the device with that address received that it's getting communicated with and is ready. And then if it's not a 0, that means it's not an acknowledge. That means either the data, something came through faulty, or in the case of when you're sending the address, it would mean that that address is like either not available or just doesn't exist in your network. So you're trying to write to a device that is not connected. So that's the address frame. For our purposes today, again, we're only going to be sending just 7 bits of address data. We're not going to be using the read or write, and we're not going to be using the acknowledge or not acknowledge. And then after, so it goes start bit, technically a 9-bit data frame where the first 7 are the address, then read, then write, and then acknowledge or not acknowledge. And then immediately after that frame we start writing data. And the data frame is a little less complicated. So it's just 8 bits. any data transaction, it has to be 1 byte long or 8 bits. And so immediately after address, you start writing your 8 bits, and very similar to address, at the positive edge of the SCL signal, you sample SDA, and then that just gets your value of the data you're trying to write. And so in our simplified version today, we're going to be writing 1 byte of data, and then we're going to immediately end and send a stop bit. In I2C normally, that you can send as many bytes, so you would have 1 start transaction and then send it to what address you're doing, and then you would just continue writing the data in 8 bits at a time for however much data you want to write until you finally write a stop bit saying you're done with the transaction. For us today, it's just going to be 1 byte of data, and then we're going to immediately stop. And just like the address bit, the 9th bit is the acknowledge or not acknowledge. So in the case of data, it would be if the slave read only 7 bits of data, it would be not acknowledged. That was not full. But otherwise, it's not used in our simplified version. It's just in a fully implemented version. So that's the data. And then once you're done sending your data, you send a stop bit. So for us today, we're writing 1 byte and stopping. The actual full I2C protocol, you send as many bytes as you want and then stop. So that is that's the full thing, right? So we have a start bit, send addresses, and then read, write, acknowledge, and then as many bytes of data as we want until we're done. So just to go back and give you an idea, a full I2C transaction will look something like this waveform. So we'll have a start bit, which is in this blue rectangle, and then we'll have the 7 bits of address read off of SDA, read, write, acknowledge, and then as many data bits as you want, so on and so forth, until you finally have the stop bit, which is in this red rectangle. So yeah, that's any questions on what each part of I2C is and what this waveform is going to look like, I guess. Oh, and I accidentally popped up my keyboard left arrow, so we're going back until it's in. All right. All right, so if there's no questions, I got one more thing, and this is just a simplified master state machine for you guys. So we're going to be, anytime we're in idle, we're just going to hold SDA and SCL. I know that is written SCK, that's a typo on my end. So we're going to hold SDA and SCL high the whole time. And then based on our start signal, we're going to write a start bit. And then immediately after the start bit, every single positive edge of the clock on SCL, we're going to be writing an address bit, 7 of them, and then we'll move on to the 8 bits of data, and then we're going to stop. So this is a simplified version. This doesn't have the ability to do things based on your read and write, doesn't have the ability to do things based on your acknowledge or not acknowledge, and it also does not have the functionality to continue to write more than 1 byte at a time. Which honestly, for the most part, I2C transactions, probably 80% of all I2C transactions are just 1 byte at a time. So that's not a super big limitation, but it does give you guys a little idea that whatever we're going to be implementing today is not fully done. And I will give you guys some suggestions and pointers if you want to continue implementing it. Okay, so next up, if you guys don't have any last questions on I2C, what it's good for, what it's used for, or just what it's going to look like, we're going to start programming. So any questions before we move on to programming? Give you guys 10 seconds or so to think of anything. Alrighty. Does not sound like we have any questions. So let's get into some programming. Oh, this is our continuing forward anything. Okay, so let's make a new project today. So in part 1, we went over, oh, by the way, can you guys see Quartus here before I start doing anything?
Yeah.
Awesome. Okay, so in the beginning, or part 1, I showed you guys how to make a project in Quartus and stuff. So I'm not going to go over it super in depth, but obviously you guys have to see me make it. So let's put this in, oh, wrong desktop. I'll make a new folder here called demo. And then let's call this, our top level is just going to be demo. It doesn't really matter what the name is. We make an empty project, no new files, doesn't matter what device we choose because we're just simulating today. And then we're going to do all our simulation in Model Sim Altera with System Verilog. Okie dokie. Yeah, I'm so, guys, there's like 0% chance that I fully program this thing working just like live. There's going to be some debugging today. All right, so we have to make sure our top level module is the same name as our project. So we got I2C demo, file not found. What? Aren't I making it? Oh, did I click open? I might have clicked open. Yeah, that I did. All right, so we're making a new system Verilog file. And let's go ahead and make this our top level. Okie dokie. So this is our top level. So we have to make sure our module is the same name as our file name. This is just the basic syntax for making a module. So everything in between here will be in our module. Okay, so based on our state machine, let's go back and look. I think we have it here. So what do we need? So we'll need a start signal. Here we go. Well, first of all, we're definitely going to need a clock. We almost always need a clock. So input will have a clock. Always a good idea to have a reset for your device. And then it looks like the only other input signal we needed was a start, which will just tell us when we want to start sending our information. And then we will also need the input of the data and address we're going to be using. So we'll have, sorry, I think I have these in the wrong order. I guarantee I'm going to make some mistakes like this. So it should be input, logic, and then so we need a 7-bit wide address. So most significant bit will be 6 down to 0. We'll call it input address. I guess we'll also call this input start. And then we also need another input for our data. This one's going to be 8 bits wide, so 7 down to 0. Data. And do we need any other inputs? We have the start, address would be an input, data would be an input. For our purposes, I guess we don't really need to stop. If you were going with like a fully implemented something, you would need to stop to tell you when like the data that you've just sent in, like when it's done. But for us, we're just going to stop at the end of one cycle, so it doesn't really matter. So I don't think we need a stop input signal. So now we need to do our outputs. Like back to here. So our outputs, we definitely need SDA and SCL. Those are the main two, right? I don't think we need any other outputs. I'm going to add one more though, just a done signal to help us when we simulate this. To let us like finish our test bench nicely. Oh, sorry, not inputs. So these will be the outputs. So we'll have an SDA, an SCL, and then we'll also have a done signal. Okay, so I think those are all the inputs and outputs we're going to need for this module. So let's go ahead and add some local variables now. So I know we're going to need something to keep track of our states. So we are coming back here. We have 1, 2, 3, 4, 5 states. So we're going to need 3 bits to represent a number that's 5 long, or value 5. So 2 down to 0. And so we have an idle state. We'll call it 0. We had a start state. Call it 1. The encoding I'm doing here, by the way, is not like it. I don't remember the name. It's basically just every state, you just assign it one value higher. If we were going for real optimization or something, we could do like 1 hot encoding or like minimal encoding. I guess we kind of are doing minimal encoding here, but our encoding today is not very important. It's not what we're focused on. So the next state we have is address. And we have data. And then we have an end. I don't know if we call it stop or what. Stop will be 4. Those are our state variables, and then we need actually variables to hold those. So 2 to 0, and then we'll have a present state. So just like we learned in part 1, we'll have the present state and the next state, like logic driving us. So we have present state and next state. And then I know for our address, we're going to need a counter because we're going to be sending every clock cycle. We'll have to keep track of what bit we've sent and what bit we haven't sent yet. So we'll have a counter for that. So we'll have address and hold on, gotta know how to spell address counts. And we'll also have the same thing for our data count. I don't think we have any other variables so far. We can add them as we go as well, but I think these are the ones we'll need up front. Okay, so let's get with the first thing. First thing we do that we learned last time is that we're going to have our state driving like separate from everything. So at every positive edge of the clock, we want to transition our state. So at every pause edge, well, first, I guess we should check if it's resetting because we added a reset signal. We got to use it somewhere, and this is where it would be. So if we're resetting, let's just make our present state go to idle. If we're resetting, that's probably a good place to be. And then if we're not resetting, this is the logic behind just a finite state machine. And so just every clock cycle, we're going to calculate what our next state should be. And then at the positive edge of the clock, we'll transition to that. So what that means is every clock cycle, our present states will become our next states. And we calculate separately. Okay, so that's like the whole logic behind driving our states. It's very simple. It's always repeated as well. Like every time you're doing a finite state machine, you're pretty much going to have that same clock up there. So hopefully you guys remember that from our last part or have seen it before. Is there any questions on anything we've written so far? Okie dokie. Doesn't sound like it. I spent that whole time picking at my hand, by the way. I found a cut somewhere. All right. So we have our state logic to drive everything. So next up, let's go ahead and look at how we're going to determine what SCL is, because SCL is pretty simple to determine what it's going to be. So based on our state machine here, it looks like in the idle and start and stop states, SCL will just be held to 1. And then otherwise, the address and data states, we need the clock to mimic our clock so that we can actually use it as a clock, right? But otherwise, we won't hold it as 1. So it's only really dependent on the state. It's not really like in our calculations of next state, like SCL is not really relevant, So we're going to have this in a separate always block. And so if I did pause edge of the clock here, just like we, for the most part, do on these guys, what that would mean is that every positive edge of our clock, based on the state we're in, so let's go ahead and see what states we have. So if our present state is idle, or if our present state starts, or if our present state ends, this all just came from the state machine we just looked at. So if it's any of those 3 states, those were the states where our SCL needs to be 1. And then otherwise, so if it wasn't those states, then our SCL needed to be the clock signal. So we would just do SCL. But there's a problem with this logic, and that if we're only running this always block at the positive edge of the clock, then our SCL will never fall because every positive edge is going to get re-updated to the value of clock. And since we're doing this all on the positive edge, clock will always just be 1. So we actually need to update this every time clock changes so that we get when it's falling as well. So to do that, we just got to get rid of pause edge. So anytime clock changes, we want to do this. And so depending on what state it is, it will either basically be exactly the same as the clock, or it will just be 1. So that's the entire generation of our clock for here. Next up is the actual complicated part, which is our finite state machine. Okay, so for our finite state machine, in the past with the vending machine we worked on, we did it as a combinational block because anytime any of our input signals, which were like nickels and dimes that we were counting up, If any of those changed, then we wanted to change the state. But since none of those, or those signals were very nice in that they were high the entire time, and like it was just any time they changed, not based on a clock here. But for I2C, the states we're in, we actually want to hold, like consider the address state, right? We want to make SDA a certain value, the value of our address bit, for an entire clock cycle. So if we did it just as a combinational, it might output the value just for like a very short amount of time, and then the next clock cycle, or like the next time anything changes, it'll change what we're trying to output, which is not what we want. So for our next state logic for this, we actually want it to be driven by the pause edge of the clock. And the reason is because we want to hold our values for one whole clock cycle for I2C, so that they can actually be read, as opposed to if anything changed really quickly, it would just like fluctuate and you might not catch it. That's the logic behind that. Okay, and so our state machine, it's very similar. The syntax for a state machine is pretty much the same every single time. So you'll always have, well, I guess you can do it without cases, but the easiest way to do it is cases. Otherwise, you'll just have a bunch of nested if else's and stuff. So we're going to do a priority case of our state variable. And I think, I forget his name. He was here for like syntax, but it looks like he's not here anymore. But this is one weird syntax of System Verilog, is that the case statement, like everything else usually has like a begin and an end. The case, there's no begin, it's just end case at the very bottom. Anyways, so in our case, we need to do something for all our cases. So let's just go ahead and, I'm not gonna program them all right now, we'll do them one at a time, but I just wanna lay them out so they're all here. Address. We have data. And then we call it stop, I think. Oh, I think I made it end here. It should be stop. Yeah, it's stop. Stop in. There's no difference. And this really makes me wish that Zoom had a music bot. I just honestly wish Zoom had a music bot all the time. So I listen to music all the time. Okay, so those are all our states. And then one thing you always want to do when you're doing a state, like, or a case, what would this be called? A finite state machine switch case thing, is you want to add a default state at the end. Because if you don't, System Verilog will complain that like certain signals won't get changed every single time, and it'll assume they're a latch, and then you don't really want that. In fact, I think if you get too many latches or something, it like won't let you compile, which is really annoying. So we just need to make sure I have a default case that just does something if we're not in these cases, even though we'll never not be in these cases. Okie dokie. So now begins the hard part of this programming. Everything else has pretty much been like, it's pretty formulaic, right? We have something that drives our state. We have all the inputs and outputs we need just from the state diagram. But now we actually have to determine in each state, what are we actually going to be doing? Oh, you know what I always forget to do? And it's too late. This is being recorded. Shout out to if anybody from IEEE watches this and it's like, oh crap, Chase forgot to do the roll call sheet. I totally forgot to do the roll call sheet again. Okay, moving on. It's too late. So for our idle state, let's go ahead and look at our state machine. So the idle state, it looks like it just holds SDA and SCL to 1. So we already have SCL, all the clocks for all these states. We don't actually have to worry about it all because we have it in that separate always block. So for idle, it looks like we just need to make SDA 1. And then we also need this logic where if we get the start signal, we need to go to the next state, which is start. So idle will be a pretty easy state. So we'll make SDA 1. So let me give you guys a little quick warning that in my coding of like my version, I did all non-blocking things in this next state logic, which ends up making the state transitions take like 2 clock cycles. So we're going to do blocking assignments or blocking statements here. And hopefully that will cut down our clock cycles. But it works if you do non-blocking, you just have to get a little hacky with it. But this should be fine. So if I end up like accidentally compiling, or I guess compiling and it doesn't work because of this, I may or may not go back to non-blocking. Okay, so SDA we've set to 1. And then the only other thing we needed of our idle state is to determine if we ever need to go to the start or not. And the way we're going to do that is if our start signal is high, which again, this is just an input into the module we made. So from the test bench, if it ever goes high, that means that our next state needs to be start. And then if that start signal isn't high, we just need to loop back to idle, sit in idle forever. Okay, guys, we are 1 of 5 states in. All right, on to the next one. Or, well, really quick, does that make sense what the idle state is doing based on our state machine and stuff, what we need it to do?
Yeah.
Yeah, all right. Okay, so next up we have the start state. Is it getting like dark outside? My desk feels, maybe it's because the screen is so white, but it feels really dark right now. Okay, so back to our start state. This one, we just need to make SDA go from 1 to 0. And it looks like that's it. And then we just straight up continue to address, like there's no logic behind it. So in here, that's going to be really easy to program as well. SDA is going to be 0. And then because of our clock logic, SCL will still be 1. And then if this goes from 1 to 0, while SCL is 1, that gives us our start bit. So that's the start bit. And then the next state will be address. And there's no other thing. This is basically just a quick little stop in so that we make sure we send the start bit. And then next up is address. And this is like where the actual like logic and stuff is going to start coming in. Okay, so for our address, if we go back here and look at this. So for our address state, SDA, it looks like it loops back because we want to be writing 7 bits of address, right? And we can only write 1 bit at a time to SDA. So we're going to have to loop back to address 7 times to write this. And every single time we loop back, we're going to take a different bit of our 7-bit long address variable or input and just output it to SDA. And so we start, according to I2C, the first bit we're going to send is the most significant bit of the address. So for us, that would be the most significant bit of a variable that goes from 6 to 0. So it would be I address, and let me write it, let me delete it. So it would be I address 6. And then the next loop, we would do I address 7 or 5, and so on. So it looks like we want to keep, we have our address count, which is the variable we're going to keep count of this with, and we want to decrement it every time. If we did instead from 0 to 7, we would be basically sending the address the opposite way, like least significant bit first, which wouldn't be interpreted well. So that's why we're going to use decrementing on our address. So we'll have to set, when we come into this state, we'll have to have our address count set to something. So let's just go ahead and do that in idle. So our address count, we want to start it at the most significant bit is 6. So we're going to be doing this loop 7 times, but we want to start at the most significant value, which is 6. So our address count will start at 6 when we come into the state. And then we want to do this 7 times. So if we're going to be decrementing every time. So if we're starting at 6, we want our address value to be less than or greater than 0. And then once we go from 6 down to 0, we will have like written all 7 bits, that because 6 to 0 is 7, right? And then we want to transition out of the state. So if our address count is still greater than 0, so we're doing this less than 7 times. And in fact, I think we're going to want it to be greater than or equal to, right? Because we want to write the last 0th like value. So we want to come into this when address count is still 0. So while it's still greater than 0 or equal, because we're going to write that last one, then we want SDA to be that bit inside our input. So it'd be I_address of address counts. And then we want to decrement our address count. And then, so if we're still greater than 0, that means we're still writing addresses every time. And then once we get to 0, we'll need to change states. But every time we come into this condition where we're still greater than or equal to 0, we want to just loop back to address. So our next state should just get address every time. And then our else, i.e. we're past the value 0, we've written everything we want to. Then that's when we want to change states. We want to go to data next. Okay, let's go ahead. Because I'm not positive. Again, I'm rewriting this using non-blocking. Or wait, this would be blocking statements. So I'm not exactly sure how it's going to interact. So let's go ahead and try and simulate it and see if that does what we want it to. So we have to write something for all the other ones just to make sure that this will compile. So these aren't actually doing anything yet, but we just need to have something there. So that we can go ahead and write a test bench and try and get this to work. So let's go ahead and make our test bench file. And we will call this our I2C demo test bench. All makes sense, right? Okay, so for a test bench file, first thing we want to include is that we're going to be advancing time. So we have to make sure that we have a timescale set. So let's do 1ns per ns. So we went over timescale a little bit in the first section. It's not super relevant, honestly. It's a pretty easy concept to understand. So if you guys have questions, feel free to ask them. But basically, this just means that we're going to be advancing. So every time we do a advanced time statement in our thing, so for example, #10 means advanced 10 time units. It'll advance the time unit is 1ns, and then the precision is 1ns as well. So that means it's only calculating things every 1 nanosecond as well. Okay, so let's begin our module. Or we have a module. I2C_demo test bench. Okay, and then so in our test bench, we need to basically every input signal to our demo module that we're in the process of making, we need to simulate so that this can respond accordingly, right? So we're going to need a clock, a reset, and a start. So we'll have logic clock, reset, starts. And then we will need to have an actual address. So we will do the address. Sorry, this is the logic 6 to 0, because it's 7 bits long. We're going to make that, what do you guys want the address to be? We can choose the number here, and we'll see what it's displayed. Anybody have any fun 7-bit binary numbers they know of? All right, I'm not hearing any.
73.
70? Is that even 7 bits? Can you do that?
Yeah.
All right. So I think I'm not going to try and figure out what 73 is in binary, but I think if I write 7-bit binary number I'm pretty sure I can write the decimal number here, and it'll convert it to 7 bits of binary for me. So we'll make it 73. That might compile error, and we might have to get a binary value and like actually calculate it because someone chose a really weird one. All right, next up we have our 8-bit data. What do you guys want this one to be? It'll be an 8-bit binary number. You know what's better than 73? 74. All right, yeah. Hopefully have no more SpongeBob references in this workshop. All right, and then we also have our output signals. We have SDA, SDL, and done. Okay, so in this test bench, we're going to simulate an I2C demo module. So we have I2C demo. And so the typical like standard for this in System Verilog is to call it the design under test or whatever in the test bench that you're testing it in, so DUT. And then we got to pass in all our values and outputs and everything. So it'll be clock, reset, start, address, data, SDL, done. Let's see if those match up. So clock reset start, address, data, SDA, SCL, done. Okay, so that's the order that we have them declared in the other thing, so everything's good there. And then we need to actually drag these values and see what happens. So we'll have an initial. If you guys aren't familiar with initial, what it does is it runs the commands inside its block starting at time 0, and it runs it once. So let's set some initial values. So we want clock to start at 0. We want reset to start at 0. We're not going to reset it yet. Actually, let's start it at 1. So we open up, or we start our simulation by resetting things. We want start to start at 0. So we don't want to start initially, we want to reset first. Our address we've already set up there. So I don't think we have to do anything with that. And then let's SDA, SCL, and done are outputs of it. So the output will be calculated. Oh, we actually never, well, I guess we're in the middle of testing. We'll have to see what done is at the very end. Or we'll have to go back and edit it because it won't know what to do with done if we don't do anything. I think it might compile. Otherwise, I don't think we have to do anything. So let's go ahead. Oh, you know what else we need to do? We need to make sure we have actually like a clock going on, right? So to generate a clock, do an always block. And I just do always add, or just always. And so every 10, we're going to make it a 20 nanosecond period. So every 10 seconds, clock is going to get its opposite value. So if we start clock at 0, at 10 nanoseconds, clock will become 1, and then at 20, it'll become 0 again, and so on, and pulse forever. So that gives us our clock signal. And then, so we have to wait. We're going to hold that high for 2 clock periods. So just to make sure it resets. So a clock period is 20 nanoseconds. So we'll hold it high for 40 nanoseconds to make sure it resets. And then we need to send our module the start signal. So we'll set start equal to 1. And we need to make sure it's not resetting anymore. So reset is equal to 0. Start's equal to 1. And then, so our logic, we're not really waiting for a signal to be done or anything. We're just waiting for it time-wise so that everything gets sent. So we can just make this wait a really long time, and then it'll stop the program, or we can stop the program and go inspect what happened. I guess we can add a finish statement, which stops it after 100 nanoseconds anyways, because that should be long enough for us to send our full I2C waveform and be good to go. Okay, I think this is all we need for a test bench. We'll have to go back here. Or I guess we could try and compile now and see if I'm wrong. So let's try and compile and see if we have a waveform that makes sense. This is my least favorite part of the Quartus Prime development. Okay, 5 errors. That's not good. Okay, so in the test bench near text B. Oh yeah, I didn't like that. I think there's a way. I think if we do, I'm not going to try and fiddle around with it. Let's just go plug it into a calculator. 73 in binary. So 1001001. Okay, that is 7 bits. Shout outs to Garrett, he knows his binary. This will be 1001001. And then this will just be 1 higher, 1001010. There we go. All right, let's try this compile again and see if that was our only issue. It's probably not. There's almost no way this was the only, wait, okay, never mind. I thought that was it was done. I was like, holy guacamole, we made it. All right, we did not make it. Oh, we didn't actually get rid of any errors. Did I forget to put a semicolon or something? Oh, in here. What is it complaining about? So at line 5 near text B, expecting semicolon. Oh, I think I have the order of these swapped. Let's try that. Also, I think now that I'm realizing it as I just double click synthesis, I think our 8-bit long data is actually only 7 bits long. near text end. So that's in the actual thing. At line 56. Oh, we forgot a semicolon. I also think this is only 7 bits long. So we need to add one more 0 there. Eventually we'll get this running. You guys are getting the real system Verilog experience though. I spent so long debugging this program, dude. It's bad. All right, object start is not, oh, it's I_start. That's what we called it in here. We're gonna get this to compile. If it's the last thing I do in this workshop, which would be really bad because this is only like one state. Okay, it compiled. So now we're gonna go ahead and open up our simulation and see how the waveform looks. I don't know if you guys are familiar with Quartus Prime or any other like simulation. I'm hoping there's better, but Quartus Prime is so bad, like the workflow. Like you have to like compile everything over here, then compile it again over here.
Yeah, it gets annoying.
And then like every time you change something, you have to like recompile.
Recompile, yeah.
Okay, so the fact that I2C_demo is not there gives us a problem. It means something didn't compile in our design here. The design unit was not found. So it's in the test bench at 9, which is the line that we had probably declared that. So why would that not be found? So it's the correct name, I think. The correct ordering. And it doesn't give us any errors. This is like the worst compilation. I didn't name it iStart here. So the names here shouldn't affect each other, but we can try it. You know, I'm no master. I've definitely had dumber errors. Okay, we got 2 errors. That's probably where I was actually doing. I wish these were like the actual errors because I was surprised it gave us another error. It previously passed analysis and synthesis. See, this is the worst kind of thing because like we're like compiling. So like in theory, it should be working. What does that mean? Okay, it might be complaining that we don't drive done, maybe. I saw that in one of these. It said like done has no driver. So so the actual done like variable is really easy. We're only done once we reach the end state. So once we reach the end state, I'll do our done signal will be equal to if our state is stopped. So as soon as we're ready to stop, that means we're done. I don't think this is going to fix it. All right, it still compiles. Let's read through our warnings, see if anything happens. Output pins are stuck at VCC or ground. Don't know what that means. That's not good though. Let's try and recompile and maybe it'll fix itself. Oops. There's 0 errors or warnings, but we still don't get what we need to. So what is the one error? I think what this error means is that it's not like in the same directory as I2C_demo. I think I got this before, but that doesn't really make sense. because it's in the same directory. It is called I2C demo. Man, it's always these issues that like I wish it gave an error for, because this is hardly an error. Why is the design unit not found? Let's just close model set and maybe it'll work. I'm very doubtful though. I'll be really happy if it does work though. Dang it. Same error. Okay, let's go look back at my other code and see if I did anything different. I have nothing different in my example. Okay, a lot different because they're all non-blocking assignments, but let's try. Maybe this needs a default case. Sometimes it's recommended to do that. And then it'll change every time. If anybody sees any issues I made, by the way, feel free to tell me. Okay, it compiled again. Okay, well, no, that we always had that. What the heck, man? I literally could not tell you why this isn't working, and it apparently can't tell me either. Let's see. I don't think that's going to fix this, but we should have it anyways because we should reset it. I'm not going to spend too long trying to debug this. If we can't get it in like a couple minutes, I'm going to just jump over to the code that was working earlier today and pray that something didn't happen to make it not work. I don't know if you guys have ever done like live programming, but like code just like stops working randomly. Like it worked earlier in the day, you change nothing, come back and it just doesn't work. That would be really not cool. I don't understand. It should be found because it's in the same directory, which is what it's based on. Alrighty, y'all. We can't really simulate this. I have no reason why it wouldn't be found. So we're going to move to the example code I have, which is unfortunate. Live programming already over. Oh, my mouse is broken and I can't like slide things into the other window. I ordered it. My new mouse should be here today though. Oh, we're going to get this. Come on. Yeah. All right, we're back. So this is the master code we were working on. Like I said, everything here is a non-blocking assignment, so it's going to be a bit different than what we just did. But the logic behind it is very, very similar. It's just if I did a non-blocking, I had an extra like leave this at a certain value because it takes longer to transition the states. But the logic is the same. As long as address count is greater than 0, we're going to display that bit of address count and then decrement it. And then our next state, again, because the non-blocking is like 1 behind, I transitioned 1 state earlier. So even though we want address count to like come back when it's equal to 1, it'll still come back here. It'll just then immediately go to next state of data if it follows that logic. So that's what the logic of address is going to look like. I mean, we can compare what I did here and what I did here. It should be no different. Yeah, dude, I really have no idea why this didn't work. I should figure it out too, because I get this error so much. We don't have time to figure it out today. Okay. So let's just move to the example code. I'll just like walk you guys through the logic behind it, and then we'll see what the waveform looks like, and then we'll call it a day. Well, then I'll also go over like some improvements because this code is terrible, dude. It's some real spaghetti I plopped onto a plate here. Okay, so the logic behind address we went over as we were programming the last one, so I'm not going to go over it again. But the logic behind data we haven't gone over, but it's very, very similar. That's the same. If data count is greater than 0, we're going to display that most significant bit of data, and then decrement data. And then same idea here, because I have everything in non-blocking, I need to transition out on the last one so that we don't end up here staying here for too long. So once data is done, we'll go to the end state. Otherwise, we're just going to repeat back to data every time. It's basically the same idea behind address, but instead of displaying the address bit, we're going to display the data bit. And we're going to display 8 of them instead of 7 of them. And then the logic behind the end bit is depending on what value your last bit of data is what SDA will stay as. So in order to ensure, because the stop bit, we need to transition from 0 to 1. Like we have to go from 0 to 1 while STL is high. So in our end state here, first I make sure that SDA is 0 so that the next time through we can transition to 1. And then once it transitions to 1, we can go back to idle and just stay in idle. And then this I just set, because once we're done with that done state and we've generated the stop bit is when we should be done. So otherwise, all of the code is the exact same here, except for the non-blocking. So let's go ahead and compile this one. And also, I'll go over the test bench. It's literally the exact same, which is different numbers, because I don't think I chose the numbers here it suggested. But it's otherwise exactly the same. So then, let us compile. So we want this. Oh no. Oh, too many port connections. Expected 8, found 9. Maybe that was our issue, because this is actually an error from. Wait, no, it's not. This is the same. Bro, I'm going to be so sad if my demo code is somehow now broken. All right, let's close this so that I don't get any interference from, because that might have been an issue with the last test bench we just wrote. Not entirely positive. I think it might have possibly overridden something. Okay, let's compile this. Bruh. Okay, in the test bench, too many port connections, expected 8, found 9. That's at least an error, you know, that's so nice to see. It's refreshing. Okay, 1, 2, 3, 4. Oh yes, I forgot to edit my code. See, this is actually a programmer error and not something random going on. In the past, I had the read write bit, but I got rid of it because I wasn't actually using it. So I just had to get rid of that. It might actually complain. I think I set read write bit. Yeah, probably going to complain about that. No, looks like it didn't. Okay, compile again. Oh, here we go. We actually have a waveform to show everyone. Okay, so the logic for what we're generating, what we were just talking about with the address and data, is just this SDA and SCL line down here, which makes sense. That's what we were trying to drive. So at every positive edge of the clock of SCL, or aka the clock, it's the same thing for us. It's going to take the most significant bit decreasing of the address. So at this positive edge, we have SDA 0, and then we can actually move by positive edges. So SDA is 1, 0, 1, 0, 1, 0, which is our address that we were trying to send. So 0, 1, 0, 1, 0, 1, 0. And then there in the logic, because it takes 1 clock cycle, this is where the ACK-NACK bit would go, by the way. It takes 1 clock cycle to transition from our address to our data that we're sending. So the next clock cycle, this actually isn't significant. This is where we would read that ACK-NACK. And then after that clock cycle, now that it's in data, now it starts writing the data using the same logic we just had for address, but it's going to be 8 bits now. So now we have 1, 0, 0, 1, 1, 1, 0, 1, which is our address, 1, 0, 0, 1, 1, 1, 0, 1. Yep. And then once it's done writing that data, we then transition in our code. We go from, so we're done writing our data. So now we go down to end, and we set our SDA to 0, which if we look at the waveform. So once we're done writing the data, which is all the way over here, apparently. Yeah, because it's at the next positive edge. It takes 1, so once we're done writing the data, it takes 1 clock cycle to get into the end state, and then it takes another clock cycle to actually write our values, because I'm doing all this non-blocking things, which is not a good idea, by the way, definitely blocking. So then it sets SDA to 0 like we're intending, and the next clock cycle it sets it back to 1, which is our stop bit, which generates our done cycle down here. And it terminated exactly there because that's the logic we had in our test bench. Is as soon as we had, this is the wrong one. As soon as we had our done signal pop up, we were going to finish. I didn't implement that in the last one because we didn't do the done signal, but it makes sense that that's when we should finish, right? Okay, so that is the logic for the master, right? So do you guys understand how we took our state machine? So here, how we took our states, added states into a finite state machine, and then did basically what each state was telling us. Does that part make sense?
Yeah.
There's only 2 of you guys. So Sam said yeah. Kira, anything?
Yeah.
Awesome. So that's the entire logic behind the master. So while we're on the topic of the master, let me go ahead and talk a little bit about some of the shortcomings of this design. So the first one I've been mentioning to you guys is the whole time I did inside these states non-blocking. If you just change these, it saves you a clock cycle, and you don't have to do this weird if address count equals 1 thing. So I'd recommend anytime you guys are doing a finite state machine, I definitely messed up by doing this. You're not supposed to do non-blocking in the next state logic. You're supposed to do blocking so that it immediately transitions. Okay, so yeah, that's the first shortcoming. The other thing, well, there's a lot of things. I have some suggested improvements for you guys if you guys are actually interested in implementing these. It's going to be a lot of work, by the way. This ended up being way more debugging and stuff to get this working than I thought it would be. And you might be a better system Verilog programmer than me. It's definitely possible. Not I'm the greatest at this, but I like it. So the first implementation I want to cover with you guys is that there's kind of 2 different lines of thought for doing these I2C things. One is that you do all the logic based on the SCL signal, which is actually, I think, after implementing it that way, I think that's the worst way to do it, because it doesn't allow you to do a lot of the things that you need to do easily. So for example, I mentioned a little bit when we were in the notes, in I2C, the value that you're trying to send for SDA has to be held constant the entire clock, while the clock is high. And so if you're changing your SDA values at the positive edge of the clock, that's technically not up to the spec of I2C. because you're technically changing SDA while like SCL is high, because they both would go high at the same time. So a way to get around that is instead of basing like changing your SDA on the clock signal you're given, you can instead slow down SCL like by stretching the clock, by basically like you would just add like a counter in your clock so that SCL only changes like every other clock cycle of your original clock, which would make then the clock period of SCL twice as long as a result, which would allow you to, based on the positive edge of your original faster clock signal, write the SDA values even when SCL is low, which is what we would need to do. So that's something that could be implemented. Another thing that could be implemented, the entire code I have written here is we're technically forcing, or we're driving SDA to the value 1, whereas technically in I2C, we're not reading a voltage value of 1, we're reading a high impedance as a high value. In system Verilog, you can actually do that. So instead of giving like a value 1, you can instead write, I think high impedance is Z. So that one's a pretty small change. You could actually just like probably like Control F and like change everything. So technically what I have currently with like the 1s and 0s is not up to spec because of that. And then obviously there's a bunch of features that I left out in order to simplify it, because it adds, basically when you add the read and write, based on whatever the last bit of your address you're writing, it entirely changes which direction your state machine needs to go in, and then what like the states do as a result. So for sake of time, I didn't add the read or write functionality. But if you were doing read or write, you would basically, if you're reading from the master, you would basically implement the logic we're going to write for the slave in a minute. And then if you're writing from the master, it would be the logic we currently have. So that one's like not conceptually hard, it's just more work. And then obviously we didn't actually do anything with the ACMAC stuff. So really quick, I want to show you guys, if you were to try and like actually use acknowledge and not acknowledge bits, that means that your master and your slave both have to be able to write to SDA. So currently the way we have it, SDA is actually only an output of master, and the slave actually will only have it as an input, which means that the slave couldn't write to SDA, and vice versa, the master couldn't read from SDA. So the way to fix that is there is a type of variable in system Verilog called an in-out, which allows you to both read and write from it. And then you would change your logic based on your read and write states, whether you're going to read from it or write from it or stuff like that. So you can implement ACK and NAP in your thing. I, again, didn't have the time. And then the final thing is right now we're only writing 1 byte, which is honestly not horrible. For the most part, every I2C transaction is really only doing 1 byte at a time anyways. But if you wanted a fully developed like I2C module, you'd have to add in something that would allow you to continue to write data or stop whenever. So whether you're continuing writing or restarting. So our current implementation of the I2C master is super basic. We can only write to the slave. And we don't actually follow the logic of like high impedance and keeping it high for certain clock cycles. So there's a lot of room for improvement if you guys are actually interested in it. And feel free if you guys actually like end up working on it, to like email me or message me on Discord or something if you have questions. You'll probably know better than I would have to debug all of this myself as well. Like there's no way I'll get it first try. But yeah, so those are just some suggested improvements and shortcomings of I2C master. But the logic we have currently, you guys are good on, right? I think you guys both said yes to that. So I won't wait around. Okay, cool. So next, let's look at what the slave would look like. And our slave, again, it's going to be very similar to the master. It's going to be a bunch of shortcomings, mainly related to there's no read or write or acknowledge or not acknowledge. But yeah, the logic is going to be very, very similar. The one thing I want to cover is, so basically everything else is the same. Like it has pretty much the same, the inputs are the outputs of the other one, minus we also have a reset. And then it'll have, the slave will have its own internal address to, if you were actually adding Whether you were sending ACK-NACK bits, that would mean the slave would, if it doesn't match, or the address it reads doesn't match the address on board, is when you would send an ACK or a NACK. And the same thing for the slave data. Like this is what you would read off of, and you could send an ACK or a NACK. And then otherwise, it's all pretty much the same variables. And same thing with like generating the present state. And we'll get into the states here in a second. The one thing I want to cover with you guys, though, is I spent genuinely like 4 hours trying to figure out like these two lines. God, they're so complex. Okay. So when I was mentioning a second ago on the master side, where you can like oversample a clock, and then like it allows you to write your SDA values according to the I2C spec, and it's definitely just a better way to go. There's that same kind of logic on the slave side, and that there's two different ways to think about it. You can either treat the input SCL as your clock for the slave, which will give certain limitations, or you can also bring in an external clock that would be faster than the SCL clock, and then base your logic around that as well. So the current implementation I have is all based around just the SCL clock, like whatever comes in is the clock we're going to use. Which its shortcoming is when you're trying to detect those start and stop bits, you can't like use SCL as a clock. Like you can't use logic there at all, because it's not a clock yet. It's just one value, meaning you wouldn't like be able to do things with it. So the way to get around that is you have to do some form of combinational logic to detect a start and stop bit. So that's what these two lines are. And they are very complex. I did not come up with these on my own, by the way. I found these online and I was like, oh, wow, that makes no sense. So I'm going to try and explain it to you guys, and feel free to ask questions as we go. But perhaps the best way to look at it is going to be on a waveform. So let me actually simulate this. All right, here. Okay, that didn't go well. All right, we'll get to that in a minute. I'll just try and explain it and then we'll look at a simulation. But basically, the combinational logic is we're just trying to find a change in SDA when SCL is still high. So what that means is, in order to find a change, we'll have to record one value of SDA. So that's what this SDA shadow does. So as long as the clock is low, we just want SDA, or our SDA shadow, to just follow SDA, because as long as the clock is low, we know we're not going to be detecting a start or stop bit, so we don't need to worry about it. But if the clock is high, that's when we need to possibly detect if there's a start or stop bit, and possibly need to save or like keep an old value of SDA to find that change. So if you guys aren't familiar with this format, by the way, this is called a ternary operator. Oops. So a ternary operator is, it has a condition in front of it. So for example, we'll do like A or B. And so then there's a question mark, and then there's two statements. So if it's true, you do this. And if it's false, you do the other thing. So what this does is it actually evaluates this condition. If this condition evaluates to true, or the value 1, it will like take this value will be set for whatever you're doing this ternary operator for. And vice versa, if this condition evaluates to false, it will set the second thing. So up here, what that means is this OR statement, the OR of the not of SCL. So if SCL is ever 0, this value will always be 1. And SDA will always take the value of SDA. And if this value, in order for it to be 0, we both need the clock to be high, and we need this value start or stop that we're going to get to in a second to be low. So if the clock is high and this value is low, then SDA will take on the value SDA shadow instead of SDA. Ooh, I've been talking for a long time. My throat can feel it. Okay. So what that means is, what this is doing essentially is, as long as the clock is low, SDA is just going to perfectly follow SDA. If the clock is high and we haven't detected a start or stop, we're going to keep the same value of SDA shadow. So what that means for us is on the falling edge. I guess we have some notes here, right? Let me read them so that I don't mistake it. So at a rising edge of SCL, technically SDA, according to the spec of I2C, should rise before the SCL. And it also, even though we have it programmed not exactly that way, for some reason System Verilog still interprets SDA as rising before SCL, even though we're setting them at the same time. So at a rising edge of SCL, that means SCL is going to be 1. So this value can be 0. And start or stop will be 1, or it'll be 0 because we're on the rising edge of SCL. So this value will be 1. So it'll always be a value of 0. That means both of these will keep value 0. So on a falling edge, that means SDA or SDA shadow will essentially lag 1 like value behind SDA because it'll be set, because both of those things are low. It'll be set to its previous value, which will be 1 behind SDA, which just changed. So on falling edges, SDA shadow will be different than SDA. Which means down here in our start or stop, what this is saying is if the clock is ever high, then start or stop is this is the XOR operator between SDA and SDA shadow. This is basically saying if SDA and SDA shadow are not the same, then start or stop will become 1. So on a falling edge, SDA shadow is it's gonna like lag behind a little bit. And so then start or stop will become, or this value on a falling edge will like, start or stop will be get the XOR of those values. So if they're different, it'll become 1. Which means then it'll take up its new value. But because as soon as that becomes 1, that means that SDA and SDA shadow were different, which means at a falling edge, basically they didn't change. Or for in our practice in detecting a start or stop bit on that falling or rising edge of SDA, while SCL is 1, start or stop will go high because of that reasoning. And then we're going to use that signal, start or stop, to determine if we're starting or not. It's very complicated. And like, it seems really weird because they're like codependent on each other. Like start or stop is based on the value of SDA shadow, which is based on the value of start or stop. So it's very odd logic here. But if we go ahead and compile and we can run through the logic again, looking at a waveform where hopefully it'll make a little more sense. You'll see that it does detect the start and stop conditions. Okay, we got 2 errors. What did I do wrong? Headline 61. Oh, yeah, can't leave that in there. That's pretty bad. Okay. You guys get to see how, I don't know, you guys have probably worked in Quartus Prime if you're here at this workshop at this point. You can see how aggravating it is to work and how slow it is. Okay, let's add all of our waves, and then let's also add in our design under test, we want to add these values to show how they behave. And let's make this easy on ourselves by moving SDA and SCL down so we can compare 1-to-1. Okay, so what we're looking at, like I mentioned a little bit, on these, when SCL is 1 and we get a falling edge of SDA, it lags behind by 1 value. And so you can see that SDA, this is the actual value SDA, whereas SDA shadow is, there's this little gap right here at 1 extra little nanosecond of time precision that we have, where it lags behind that value. And because it lags behind, because start and stop is based on the XOR, basically if these values are different, it'll become high in the next 1 nanosecond because there's a little delay on it. So it detects that falling edge of SDA when SCL is high and gives us a starter stop there. And then likewise, when we have a stop condition, it actually doesn't detect it because we end the simulation too soon because our stop condition, or our simulation ends as soon as we're sending the stop condition. But it also detects, it would detect the stop as well. I don't know what just happened there. So yeah, it's very odd logic, and it's very tricky, but it's basically a combinational checking if there's any change in SDA while SCL is high by keeping a previous value of SDA anytime it's a falling or rising edge. Okay, so that's the hardest part of the slave logic. So then once you have that, you just use your start or stop to determine if you're going to start or stop. And then if you're starting, then you actually jump into this state machine. And so initially it's at idle. We're just setting up our initial values, and then it's similar to our other idle state where if we detect a start, in this case, the start comes from that combination logic, and the last one it came as a signal to our module. So if we detect that start, we're going to go to the address state. In this case, because I had everything non-blocking, I needed to catch that first address bit. So I actually read the first one in idle. If you got rid of the non-blocking assignments, I think you can actually fix this and not have to do that. But I am not a smart man. So from idle, if you get the start bit, you go to address, and then address is basically the exact same as our master module was, except instead of setting SDA to our address bit, we're going to set our address bit to SDA. That's what it means to read from SDA, right? So otherwise, it's the exact same logic. It's basically just this one line we swap. Instead of SDA gets our address bit, it's our address bit gets our SDA. And otherwise, it's the exact same logic. So we just read in 7 address bits by decrementing our address count. And then once we're done, we'll transition to data, do the exact same thing, except into our data variable now, and read them out. And then once we're done, we go transition back to idle. So the slave is actually not much different than the master. Once you have the master working, you kind of have the logic down for I²C. The hardest part is just that ability to detect the start or stop bit. And again, if you oversample your clock, or actually not oversample, you just add in a faster clock into your slave, you can actually just sample SDA on that faster clock. And you don't have to like do all this complex combinational logic. It'll be just like normal logic we're used to. Whew, my throat hurts from all this talking. But yeah, that's the logic behind the slave. It's very, very similar to the master. The hard part is just once you catching that start condition so that you actually know to start reading address bits and data bits. But then once you do that, let me zoom out a little, or wait, zoom. All right, you know what, hold on, let's just clear everything. This will reset the axes. Awesome. No, it didn't, dang it. Why won't it let me zoom out? Here we go. There we go. That's what our waveform looks like. And then so it actually like reads in. I guess we could actually show. I didn't actually show the internal what it's reading. So let's actually add these to the wave and make sure it's reading correctly. So it reads it in one bit at a time. So read in, read in, read in. And then at the end of address, so this is actually the last value of address being written. So then the next clock cycle is when that value actually is like got because of I have that non-blocking logic that doesn't work. So at the very end of address, it correctly read in the address. This is actually what we read into the internal value in the slave, which matches the address that we were trying to write from the master. So that's good news with that logic. And then the same thing for data. This is the last bit of data, and then one more clock cycle after is when this value is actually fully completed, and you can see it matches our value we were trying to write from the slave and then what we actually read into the slave. So it is a very simplified version of I²C without all the bells and whistles that honestly make I²C nice. but it gives you guys a little bit of insight, hopefully, into what I squared C is, and then like kind of what the waveforms are going to look like and how you might be able to, using a state machine, do those waveforms. Whew, it's 4:34. We made it. The rest of this workshop, I was just going to cover with you guys like the shortcomings of these designs. So like I mentioned in the slate or the master, all of those shortcomings. In the slave design, definitely want to switch from using SCL as our clock to an input clock. That way you don't have to do this weird combinational logic. You're able to write SDA in low cycles as they should be. The slave obviously needs to add functionality to read or to write, which we didn't do. And then if you change the non-blocking in our finite state machine, it'll allow you to save some clock cycles. So that definitely would be a good implementation. And then obviously the slave also doesn't have an acknowledge or not acknowledge to it as well. So in the current setup, honestly, neither of these could really be considered like a full I2C module, but you can see that they're definitely a start. We got a nice I2C waveform we were able to read and write from. So it's a good start. Whew. So did you guys have any questions on like the logic of this and like how it all works out? I'll take that as a no. Okay. If you guys didn't have questions about logic, that was all I wanted to show you guys, all the live program. Sorry, the live programming didn't work out, by the way. I honestly could not tell you what this issue is. It doesn't give any errors. That's the worst part. But yeah, so last stuff I wanted to show you guys. Oops, that's not what I meant to do. Wait, I clicked the same button. Here's just some extra resources for you guys. I think I could probably share the slides on the Discord would be the best way to go. But just some extra resources. So here is a website that goes over about the in-out ports if you wanted to implement ACK and NAC and how you might actually be able to implement that into your module. Here's just a general I2C introduction in case you like all the stuff we went over today wasn't enough. And then this is actually the website where I got that example like combinational logic for detecting the start and stop bit, which is not a good design, but here's some example code. And this, the I2C master example code, this is actually really solid code. It uses like the oversampled clock and stuff. So I'd really recommend if you're interested in like implementing your own I2C, take a look at this and like see exactly how they're implementing it. It's very nicely like commented as well. I think very clear code. So honestly, maybe more helpful than my workshop, but you know what? You know how you got that resource? Come into this workshop. Otherwise, if you guys, again, if you want to go review like how does the master or slave accomplish what it wants or any basics about I2C or anything, I'll stick around until 5. But otherwise, I have nothing else to add for this workshop besides if it interested you, if you think you want to go ahead and improve my very terrible spaghetti code design, feel free to. You guys, I think my email is available on the IEEE Discord. If not, I can put it in the chat here. It's what you guys can reach me on Discord in the IEEE Discord. If you guys do actually end up going for it. Oh wait, there's a bunch of comments in the chat that didn't show up for me. Oh, here like an hour ago. Oh, Rippy doesn't have chat up. Okay, so the positive edge of a clock. I know I'm super late on this. Oh, I think Yaret answered it. Yeah, when the clock transitions from 0 to 1. Yeah. So just anytime it rises up, it's considered the positive edge. And the negative edge is when it goes down. So yeah, I'll put my email in the chat if you guys actually do decide to go forward and like implement some of the stuff on this. But otherwise, that's all I got. Thanks for coming. Again, I'll stick around until 5 if you guys have more questions or anything. We can try to cover some stuff. me try. I don't know why the chat didn't show up.
Is it going to be posted on the same YouTube channel as the last one was posted on?
Yes, I think it takes about a day because Zoom has to like upload the video and stuff. But yes, this will be posted. I made sure to hit record. I forgot to mention at the beginning, but this was recorded.
Cool.
I think it tells you. If I hit record, you guys have to like click accept, I think.
Yeah. Okay, thank you so much.
No problem. Thanks for coming. Good luck with all your system Verilog learning.
Thank
Yeah,
you.
thanks. Bye.
Adios.